This lecture provides an introduction to different types of maps and highlights a few points on how to critically read maps. The first point to emphasize is that maps are models. That is, maps are simplified representations of reality. They are not a complete copy of reality itself. If you're familiar with the Argentine writer Jorge Luis Borges, you might have seen this very short story titled On Exactitude in Science, which was published in 1946. It's attributed to be a section of an imaginary text written in 1658. The story is 1 paragraph long. Please pause this video and read the story now. As you can see, the story describes a map that was the same size as the territory it represented. It contained all the same details point for point, and this map was useless. In his book How to Lie with Maps, Marc Monmonier writes, "To portray meaningful relationships for a complex three-dimensional world on a flat sheet of paper or video screen, a map must distort reality. As a scale model, the map must use symbols that almost always are proportionally much bigger or thicker than the features they represent. To avoid hiding critical information in a fog of detail, the map must offer a selective, incomplete view of reality. There's no escape from the cartographic paradox. To present a useful and truthful picture, an accurate map must tell white lies." So let's look at some examples of these map distortions. The ways that cartographers omit or simplify information on maps, the ways that scale is represented, the need for map projections, and ways that data can be represented on thematic maps. In order to be useful and legible, a map must present a simplified version of reality. In this image, you see a comparison of Apple Maps and Google Maps, centered on the same location and zooming in or changing scale. One cartographer compared these maps at various scales to see how Google and Apple represented content such as roads, transit, landmarks, and other labeling details. This is important because both maps are the default on their respective operating systems, and they also provide the base platform for many applications. These maps are very influential in the type and amount of information that's available to users, which in turn could influence how people navigate and the places where people visit. So he found that there's variation in the number of roads that are shown at different scales. And there's also variation in the types of places that are represented. If you're looking for more transit information, you may want to use Google Maps. If you're looking for places like parks, coffee shops, or museums, you might find Apple Maps more useful. I mentioned those variations were compared across different scales as the user zoomed in or zoomed out on the map. Map scale refers to the aerial extent that is represented. It's a ratio of map units to Earth units. So look at the map scale for the upper image, the contiguous United States, shown here as a fraction, 1 to 31,680,000. If you measured 1 inch on the map, that would represent 31,680,000 inches on the surface of the Earth. And it would be the same for centimeters, millimeters. There are no units listed because it's understood that as a ratio, the units are the same. This scale could also be represented as a written scale, where the units are converted to one more readily visualized. 1 inch on the map equals 500 miles on the Earth. If we were to zoom in on the map all the way to look more closely at the island of Manhattan, as in the bottom image, here's how the fractional scale would change. Now the fraction says 1 to 506,880. So 1 inch on the map represents 506,880 inches, or the written scale, 1 inch now represents 8 miles. Remember, map scale is a ratio of map units to Earth units. So when we're looking at a large area as the contiguous United States, the bottom number in the fractional scale, the Earth units, is quite a large number, 31 million. If we zoom in to see a smaller area, the denominator in the fractional scale also becomes smaller. It's 506,000 in this example. We refer to these differently scaled maps in relative terms as small scale maps that show larger areas with very little detail. And it's small scale because if your house was on that map, it would be very tiny. Or large scale maps where you zoom in to see a much smaller area and more detail, and your house would appear bigger as you zoom in. Here's another example. On the left in figure 4a, the map scale is 1 to 24,000. 1 inch on the map represents the distance of 24,000 inches on the Earth or 2,000 feet on the Earth. Here we see a relatively small area with some detail. We can even see individual buildings. As we move to the right to figure 4b and 4c, we're seeing more and more area on the ground as if we're zooming out. Note that in 4c, all the way on the right, the scale is now 1 to 250,000, and 1 inch on the map represents nearly 4 miles on the ground. This would be a smaller scale map as individual features on the ground become smaller and smaller, while more area overall is shown. All right, and map projections. So imagine you have an orange and you want to remove the orange peel in one piece to make the orange peel lie flat on the surface of your kitchen table. How can you present the three-dimensional orange peel as a flat two-dimensional surface without changing the information on the peel beyond recognition? In order to make the orange peel lie flat, you would have to stretch it or tear it, and this changes the information on the surface of the peel. So it is with representing the surface of the Earth. Map projection is the mathematical process of transforming three-dimensional data from the surface of the Earth to two-dimensional flat representation in a systematic way. So geographers have a saying, all maps lie flat and all flat maps lie. All maps have some distortion in shape, size, distance, or direction, just as the orange peel must be stretched or cut in order to make it lie flat. Map projections make these changes in systematic ways, so it's helpful to know something about where and how map distortions can be found on particular types of maps. One way to understand classes of map projections is to think of transferring information from the Earth or from a globe onto a flat piece of paper that would be folded or wrapped around the globe in a particular way. A cylindrical class projection would be obtained by wrapping a map around the globe into a cylindrical shape. This yields a rectangular shaped map with lines of latitude and longitude as straight lines that meet at right angles. This piece of paper would touch the globe all the way around at the middle part of the map along the equator. This is the standard line where the paper is touching the globe, and this is the part of the map that would have no distortion. The farther away from the standard line, in this case from the equator, that you would move on the map, there would be more distortion. In this case, shape of land masses is preserved, but the size of land masses would become distorted. The Mercator map is a cylindrical projection that was first presented in 1569 by the Flemish cartographer Gerardus Mercator. It has angular fidelity and preserves the shape of the land masses, the shape of the coastlines, so it was useful for ocean navigation. Size is correct along the equator, along the standard line, but there's more and more distortion in size the farther away that you move from the equator on the map. So to understand this, locate the North Pole on this map, right? 90 degrees north, the North Pole. The North Pole is a point, but on this map, it is represented as a line that is the same length as the equator. So in this case, not only is the North Pole stretched from a point to a line, but this also changes the shape of the land masses at higher latitudes away from the equator. Look at Greenland on this map. It looks to be roughly the same size as the continent of Africa, but in reality, Greenland is about 14 times smaller than Africa. Imagine folding a piece of paper into a cone and placing it over the globe. The conic class projection is often used to represent the contiguous United States because it results in a standard line in the mid-latitudes. Here, lines of latitude appear curved. An azimuthal projection would be akin to touching a flat piece of paper against the globe so that it touches the globe only at a single point. and that central point would be the only area on the map without distortion. This type of projection is often used to map the North Pole or the South Pole, but it can also be oriented at an oblique angle. Note how the appearance of the graticule, the grid system of latitude and longitude, changes with these various orientations. Cartographers generally distinguish between two types of maps: general reference maps and thematic maps. Reference maps are used to show the location of spatial phenomena, and thematic maps, or statistical maps, show the spatial distribution of one or more attributes or variables. Let's look at some examples of ways that data can be represented in thematic maps. A choropleth map uses a color scheme or a grayscale to show intensity or concentration of a variable. In this case, the percent of the population that is African American in the United States based on the 2010 census. The geographic units are colored or filled in on this map. In this case, we have counties, and the level of aggregation can be changed. We'll see an example of a state level choropleth map in the next slide. We'll also see how other variables can change the appearance of the map: the number of data classes, the placement of breakpoints between these classes, and even the color scheme choice. So each of the maps that we'll see next are going to all use the same data set from the 2010 census, and we'll see how our cartographer could make very different maps that give viewers different impressions. So here's the state level choropleth map of the percentage of the population that is African American in the United States, using the same data from the 2010 U.S. Census. We've changed the level of aggregation from the county to the state level. So the southeastern United States still stands out as having the highest concentration of African Americans, but less geographic detail is visible now that we're looking at larger areas, the states, instead of the counties. Note that the states are grouped into 4 classes. The breakpoints between each class are set to equal frequency. That is, there are approximately the same number of states in each class or category, right? That's equal frequency. So now we're looking at 6 classes, right, instead of 4. And again, the breakpoints are still set to equal frequency, right? We have approximately the same number of states in each class or category. So here's a state-level choropleth map with 4 classes, and now the breakpoints are set to equal interval. All of the breakpoints fall according to the percent of the population that is African American, so 0 to 10%, 10 to 20%, and so on. And now with equal interval, this allows you to see more variation between the states of the American South. Changing the number of classes to 6 and keeping equal interval breakpoints really emphasizes the variation among southern states. And now we've got Mississippi standing alone, right, in the highest category. We can visualize the same data with yet another type of thematic map. A proportional symbol map is useful for showing numerical data occurring at particular point locations. The size of each symbol represents population size. This map emphasizes cities because it's displaying raw count data. Right? It's showing the number of African Americans rather than the intensity of data, the percentage of the population that is African American, as shown in the choropleth map. Right? Chicago, Detroit, and Los Angeles all stand out on this map, whereas they were not noticeable on the choropleth maps. And finally, do not confuse the proportional symbol map with a dot map. To create a dot map, one dot is set equal to a certain amount of a phenomenon. In this case, one dot represents 5,000 people who identified on the 2010 census as African American. Right? Or we can also change that to one dot represents 50,000 people. So we've looked at just a few examples of ways that the same data can be represented in different ways on maps, giving viewers very different impressions. Keep in mind, this has been a very brief and simplified introduction. There are many different map projections, types of thematic maps, and countless mathematical and style decisions that cartographers make.